this is an example here. So starting from point A, we can go to the down and right, and we can go like this, and we can do a similar thing going to the right and then down. And in total, we're going to get 6 ways to reach point B from point A. So my question in 2 dimensions is, starting in the top left corner of a 2x2 grid and only being able to move to the right and down, there are exactly 6 routes to the bottom right corner. So how many such routes are there to a 20x20 grid? Well, okay, so what I did was I looked for a grid length of 1, 2, and 3, and I found that for n equals 1, 2, and 3, there were 2, 6, and 20 solutions respectively to get to the end. So what I ended up doing was I realized that the left edge of the grid and the top edge of the grid, there was always one way to get to any point there. But every single other point in the grid was simply the sum of the number above and the sum of the number to the left of it. So as you can see, every single number besides the ones on the top left and top edge follow the same pattern. So you might notice that this is familiar to something else. If you all tilt your heads, you can see that this is Pascal's triangle. And if you'll notice, these points actually correspond to the points on my grid right here. So before I go any further, I want to talk about combinations. And this is read as n choose r. And this is the way to find, if you have n objects and you want to arrange r of them, where order doesn't matter, that is the formula for finding that. And this exclamation mark is also called a factorial. And so n factorial, if n is an integer, this is simply n times n minus 1 times n minus 2, etc. And so 5 factorial, for example, is 5 times 4 times 3 times 2 times 1, which is 120. So on the left here, this is actually Pascal's triangle. All of these, like for example, these are all 1s, and this corresponds to the left edge of the grid, and this corresponds to the right edge of the grid. These are also all 1s. Now, if you'll notice, we can make a square using these 4 points right here, and these are the number of ways to get to any specific point on a 1x1 grid, and these are the number of ways to get to a specific point on a 2x2 grid. And as we showed earlier, this is 4 choose 2, which is 6, the number of ways that you can get to the end. And so this is just a 1x1 square that shows the number of ways to get to a specific point using combinations, and it's showing what those combinations are equivalent to. So now we come to the pattern in 2 dimensions. Basically, all of these follow the pattern of 2 in, choose in. And we're going to use that fact to find the number of solutions in a 20x20 grid. So this would be equivalent to 40 choose 20, which is 137,846,528,820. So it gets really big really quickly. Now that we've looked at 2 dimensions, let's look at 3. There is a line there which represents 1 dimension, but we're not going to look at that because it is a trivial case since there's only one way to get to any point. So let's look at a 1x1x1 in 3 dimensions. Notice that the top of this is actually a 1x1. So you can see we show the number of solutions to get to the end there, which is 2. And to get to the end here, we can go this way or this way. So there's 2 ways to get to this point. This way or this way, and there's 2 ways to get here. Or we can go this way or this way. So there are 3 places we can move to get to here. And the number of ways to get here is 2, 2, and 2. And we just add them up to find out what the number of ways to get to the end is. So I wrote a program in Python that what it's doing up top here is it's initializing in 3 dimensions every edge going down, forward, or to the right. They're all 1s because there's only 1 way to get there. What it's doing right here is this is calculating the number of ways to get to any point on the top of a 3-dimensional grid. And so now that I have that, what this is doing is simply adding, for every other point, it's adding the number above, the number to the left, and the number behind it. So it's following a similar pattern to what we had in 2 dimensions. So on the left, those are the solutions for n equals 1, 2, and 3 in 2 dimensions. And on the right are the solutions for n equals 1, 2, and 3 in 3 dimensions. And if you'll notice, every n for 2 dimensions divides the respective n for 3 dimensions. So that's a very interesting pattern. So basically the pattern in 3 dimensions is pretty similar to the one in 2 dimensions, but we're taking the solution in 2 dimensions, which is 2n shoes in, and multiplying it by this 3n shoes in. So I think you can see a pattern forming for any dimension here. And basically the pattern overall is simply n shoes in times 2n shoes in times 3n shoes in, etc., all the way to dn shoes in, where d is the number of dimensions. And this is a number of ways to get to position n, etc., from 0, 0, 0, etc. So this right here is n shoes in, and this is 2n shoes in, etc. What you'll notice is this will evaluate to 0 factorial, which is defined as 1. But every other term, you can actually cancel something out. So this n factorial here is equivalent to this 2n minus n factorial, so we can cancel those out. This 2n factorial is equivalent to this, so we can cancel those out. And we can keep doing that until the very last term. Now, since this is our final term, we don't have anything over here, so nothing to cancel out with. So as you see in the numerator, we're left with a dn factorial. And in the denominator, we're always left with an n factorial. And since there are d of these and we're multiplying, the denominator simplifies to n factorial to the d, and the numerator is just simply the numerator in the last term. So here's an actual explicit proof of what I found. So assuming we start at the position 0, 0, 0, etc., we want to get to the point n, etc., where d times n is equivalent to the sum of the n's in the latter point. We have d times n ways that we need to move to get to the end. In each of the dimensions, we can move n times in that dimension. So expressing this using combinations, we have dn shoes n ways to move in one direction. And since we've already moved in n ways, the next time we have dn minus n shoes n ways to move in another direction, and dn minus n shoes n ways to move in yet another. And this pattern just goes on, and it simplifies to what I showed earlier, to dn factorial divided by n factorial to the d. And this can also be expressed like this, where the sum of the n's on the bottom is equivalent to d times n. All right. Any questions? Okay, you.
How long did it take you to figure this out?
Oh, I probably spent a dozen hours on it. I probably spent, I looked for solutions just by hand for n equals 1, 2, and 3, etc. And I tried to find patterns in the numbers, and I couldn't do that because I wasn't thinking in terms of combinations at that point. So it didn't really become clear what the pattern was until I thought of it in terms of combinations. And it probably took me, I don't know, 3 or so hours to make the program. It was a lot of, I'm not super familiar with Python, but so it took a while for me to figure that out. My logic was good, but writing it was a whole other issue. And so yeah. Yes.
How do you feel it's going to be used in, outside of math, in the real world?
In the real world? Well, I did provide a real world example at first, like in the city grid. So if you want to know, for whatever reason, a number of ways to get to some point, you can find that out using this.
Follow-up question, can you see that being used in things like Google Maps? Like when they try to give you the fastest way to get somewhere, do you think they would move this kind of thing?
Not directly, because I'm dealing with a number of edges, but an edge could be like this big or it could be this big. So it doesn't give you an actual amount of time. So it's not directly related to that. But it could be modified. I'd have to do a lot more work to figure that out though. Yes?
So you talked about this works in any number of dimensions, 4, 5, etc. Is there any way of actually visualizing that?
Well, you can kind of visualize like a four-dimensional hypercube, but it's really hard to think about, I think,
Okay.
in terms of visualizing. I can kind of show you a method that might help you figure this out. Okay. So basically the one-dimensional analog to a square is just a straight line. So let's say we have one edge and two vertices right here. We want to move up a dimension. All we do is go like this, and that's two-dimensional. We have double the amount of vertices. If we want to go to 3 dimensions, what we do here is kind of like this, and then we connect these vertices like so. Now, if we want to go to 4 dimensions, we're going to do basically a similar process, but it's kind of hard to draw on a 2-dimensional board. But I'm going to draw another cube here. And let's see, this goes here, this goes to this, and this gets awkward to draw. Let's see. This goes here, this goes here. So that's my attempt to draw a 4-dimensional cube on a 2-dimensional surface. But you can see the process I'm using, right?
Sure. Okay.
Okay, and you can extend that to 5 dimensions, but I'm a math major, not an art major, so. Any more questions? Yes.
What are your goals to follow up what you found to maybe increase just the knowledge about paths or other applications within graph theory?
My plan is to, you could like use rectangulars and rectangular prisms. There are ways to, using combinations to figure out the number of paths to do that. So I want to look at that. Another thing I want to do is if I enable a certain amount of backtracking, like you can move back 2 edges, I want to find out how that changes things. And I think that is doable because we'd basically be taking some combinations, because every point is a combination. It would just be, I'd have to work on it for a while to figure out how that would be done. Yes?
Oh, I'm sorry. So when you're doing this, it assumes an equal length within each edge, right? And so that means that there's no necessary optimal path. It just creates all paths at an equal optimality.
If you're dealing with a problem that has edges of the same length, I mean,
Okay.
this doesn't give you a solution. If your edges vary in the real world, it doesn't really give you a solution, but because of the varying length. So, like I said, I have to modify it in some way.
That's what I was going to ask, if you could weight the edges and then calculate all the possibilities for the weights, and then you could minimize the weights on each path, right?
You could.
With Python, not by hand.
Could. Maybe that'd be something I could do next year, but I can't do it in 2 minutes.
Now.
Any more questions?